Okay, all right, nice. I should get my markers. Am I streaming? I'm gonna have this question every time because I don't have. Okay, I forgot to close my door. Okay, uh, markers. I need markers, and I also need to open my stream. That's what I was doing here. Uh, how how do I do that? Oh, here we go. Okay, I'm just gonna leave it here. So I feel like that's good. I don't know how I did that. How did I do that? It's a good thing that no one is watching. Oh, what did I just do? Okay, nice. There we go. Okay. Uh, testing, testing my microphone. You will hear people in the background. Okay, so something I noticed yesterday, not yesterday, a couple days ago while I was doing this, uh, my my computer for some reason will use my phone as a microphone when I enable Lumi on the website. Not sure why that happens, but I will figure it out. Hello, welcome. So today, what I wanted to do was use Lumi. I'm looking at OBS. I'm sorry, I don't know why I have this open. Okay. What I want to do today was use Lumi to go through some math competition problems. So one of my students, he's working on a uh, he's in a club or class that's part of a math competition. And he gave me all these questions today that we were trying to work through, and I admit some of them I was like, I don't know the easiest way to do this. So I'm gonna have Lumi teach me and see if it's any better. So let me just log in here into my one of like 8 accounts that I have on my own website. Okay, uh, so the practice problems look like this, and I know the answers are there, and I already looked, and I know the answer is 25. Like, okay, I know that I shouldn't look at them, but it's so hard. It's right there, you know. And so I'm not gonna. I'm gonna try my best not to. Oh, I'm looking at it again. Not to look at it. Not to look at the explanation. Just to look at the question and answer the question. Even though I know the answer to the first one's 25, I'm gonna get 25, but it's fine. I'm just gonna take a picture. Okay. So I guess we're doing more of the homework feature again today, but that's fine. I actually think the homework feature is one of the most important features, if of anything that the site can do. So I'm more than happy to just to keep using it. Yeah. Okay. Uh, so just like, well, I guess I should explain again. So I explained this in the first stream, but Lumi has the ability to see your work and help you with it. Now, I actually should do some where I actually write work out and take a picture of it and then upload it to see if Lumi can correct me. But we'll get there when we get there. I'm sure that'll come at some point where I do some work with one of my students and then I don't know if it's right or if I'm wrong and we don't have an answer key, and I think that'll be the time to check it. Until then, let's try to solve this problem. Let's see what Lumi has to say.
Hey Jin, welcome back. I see you've uploaded a new homework problem about digit products. This is a neat number theory problem. The digit product of 56 is 5 times 6 equals 30. And for 57, it's 5 times 7 equals 35. We need to find how many two-digit numbers have an odd digit product. What's your initial thinking on this? Any ideas about when a product of two digits would be odd?
Hey Lumi. So This is actually from one of my students. It's his work that we're working on today because for some of the problems, I didn't know how to answer them. So we'll go through it and then I'll give him this video. We're streaming again, by the way, so say hello to the stream, and then hopefully I can go back to him next week with way better explanations. Or work. But looking at this, it's a counting problem of some kind, right? Like we're counting specific numbers. So I think the first step we should do is break this into cases.
Hey, Stream. Okay, so you're working through this to help your student. I love that approach. Breaking into cases is spot on for a counting problem. Let me throw out the key insight first. When is a product of two numbers odd?
Uh, oh yeah, I was just about to say that. I think if they're both odd.
Exactly. You nailed it. So for a two-digit number to have an odd digit product, both digits must be odd. Now the question becomes, how many two-digit numbers have both digits odd? What are the odd digits we can use?
Okay. I see the way you're thinking about it, and like I think I got it. I just realized that I'm writing kind of small. Sorry, I will write bigger for the rest of it. But okay, I think that if we know it's odd times odd, we just have to count all the odd numbers. But counting would take forever, right? Like we'd have to go one, three, five. Oh, I just okay. So one, three, five, seven, and nine are the odd numbers we can use for the end of all the two-digit numbers, right?
Perfect. Yes, five odd digits. Now, here's where the counting principle saves you. Think about building a two-digit number. You need to pick a tens digit and a units digit. How many odd choices do you have for the tens place? And how many for the units place?
Is it odd? Oh, because right, we're trying to make an odd number, so both digits have to be odd. Well, it's the same thing. It's another five choices. It's one, three, five, seven, or nine.
Exactly. Five choices for tens, five choices for units. By the multiplication principle, that's 5 times 5 equals 25 two-digit numbers with an odd digit product. Does that logic track for you and your student?
Well, my student's not here. He'll have to watch the stream back at some point. But that makes sense to me. Okay, I get why the answer is 25 now. Got it. That okay. That was actually a lot easier than I was making it out to be. What was I don't know what I was thinking on this problem, but yeah. We can move on to the next one now. It says
Nice. Yeah, counting problems often look scarier.
okay. So that was actually a lot easier than I thought it was gonna be. So let's just do the second one. Uh, okay. I have to admit that I saw the answer. It's 23, but I didn't read the explanation. I didn't read the explanation. I only looked at the answer. Although I guess knowing the answer is it's like half of it, right? Like if you know the answer, you know what to work towards. But we're going for understanding here, so I'm just trying to understand the problems. Okay, let's see.
Hey, Jin, welcome back. I see you've got problem 2 now. Finding how many integers from 1 to 75 have exactly 4 factors. This is a great number theory problem. Before we dive in, quick question. Do you want to work through this one yourself with some hints? Or would you like me to walk you through the approach? Also, how'd those YouTube demos go?
Oh hey, you remember the YouTube stuff? Yeah, I uploaded the first or second or third video today. It got 4 views in an hour. I think it's pretty good for a starter. uh, Actually, yeah, I'd like to talk about how I would approach this problem, and then you just give me hints if I make mistakes.
4 views an hour is solid for early traction. Nice! Okay, let's hear your approach. How are you thinking about tackling this exactly 4 factors problem?
Well, the way I think about it is that if you have four factors in total, it must mean that the factor tree that is created out of your factors only has two levels, right? Like for example, if I took 16, I can break that up into 4 and 4, and then I can break all of those up into twos. Uh, and because it only goes to that second level, 16 has four factors. But wait, no, 16 has 1, 16, 2, 8, 4, 4. Wait, no, I'm wrong. But I feel like it's something to do with the factor trees like that.
You're on the right track thinking about prime factorization. Here's a nudge. Forget factor trees for a sec, and think about this formula. If a number has prime factorization P1, A1 times P2, A2 times PK, AK, then the number of factors is. So what prime factorization structures would give you exactly 4 factors?
Wait, hold on. You're gonna have to like write that down. I cannot follow what you just said. Uh, hmm. I'm a little confused. Can you explain this one again?
Totally hear you. Let me break it down more simply. Look at 12. Its prime factorization is 2 squared times 3 to the first power. Those exponents are 2 and 1. The formula says, take each exponent, add 1 to it, then multiply them together. So 2 plus 1 equals 3, and 1 plus 1 equals 2. Multiply 3 times 2 equals 6 factors total. And if you list them, 1, 2, 3, 4, 6, 12. That's exactly 6. Does that click better?
Oh, wait, that actually makes so much sense. You're okay. I get it. So let me try with 16. So 16 can be written as 2 to the fourth power, and so wait, but there's wait, 16 can be 2 to the fourth power. So how does that work with 16?
Perfect example. So 16 equals 2 to the fourth power. The exponent is 4. Apply the formula. 4 plus 1 equals 5. So 16 has 5 factors. Can you list them out to verify?
Five factors? Wouldn't that be? Oh, it's because four counts twice. It's four times four. Okay. So the five factors are 1, 16, 2, 8, and then 4. And you don't count 4 twice. That's why it's 5.
Exactly. You nailed it. 1, 2, 4, 8, 16. 4 is the square root, so it only gets counted once. Now, here's the key question. What prime factorization structures would give you exactly 4 factors using that formula?
Prime factor. It would be 2 to the 2 to the 1, 2 to the 1, right? Wait, no. 2 to the 1, 3 to the 1, or 2 cubed.
You're close. Let me help you think through this. We need the formula to equal 4. So what combinations of exponents, when you add 1 to each and multiply them together, give you 4. Think, what are the ways to make 4 as a product?
I mean, there's only two ways to make it, right? It's either 4 and 1 or 2 and 2. And so the prime factors have to have either both an exponent of 1 or one prime factor with an exponent of 3.
Perfect. You got both cases. Case 1, a prime cubed, like 2 cubed equals 8. Case 2, two different primes, like 2 times 3 equals 6. Now the question becomes, how many numbers from 1 to 75 fit each case?
Wait, but that's so crazy because how. Oh, okay, okay. So we would have to figure out numbers that have uh, combinations of either 3 cubed or 2 times 3.
Exactly. Let's tackle case 1 first. Numbers that are a prime cubed. What's the smallest prime, and what happens when you cube it? Can you find all the prime cubes under 75?
Oh, okay, okay, okay. Yeah, yeah, yeah. It's 1, uh 8, 27, uh wait. 1, 8, 27. Are there more?
Close. 1 isn't prime though. Remember, primes are numbers greater than 1 with only 2 factors. So you've got 8 and 27. What about the next prime, 5? Does 5 cubed work?
Isn't 5 cubed 125?
Exactly. 125 is way over 75. So for case 1, you only have 8 and 27. That's 2 numbers. Now for case 2, products of 2 different primes. This one's trickier. What's your approach for counting these?
Oh, wait. Yeah, yeah, yeah. Okay, okay. So what I would do is I would go uh wait. Hold on. That's a lot though. It's like 1, 3, 5, 7, 9, and then like all the primes up to 75.
Good instinct. Here's a smarter approach. Organize by the smaller prime. Start with 2 times other primes. How many work? Then 3 times primes bigger than 3. Then 5 times primes bigger than 5, etc. Try starting with 2. What's 2 times 3? 2 times 5? 2 times 7? Which products stay under 75?
Wait, but that would take so long. Can't Okay, I know this is a bit more advanced than this current problem, but couldn't we just do like combinatorics and think about the number of spaces and the number of options? Could that help us somehow? No, no, because we need the product. We need to know what they're equal to. Uh, is there an easier way to do that, or do I actually have to count all the primes and multiply them all together?
I love the combinatorics thinking. But you're right, we need the actual products to stay under 75, so we have to check. The systematic approach I suggested is actually the fastest. It's tedious, but only takes a couple minutes. Want to try listing them together? I'll help keep track. Start with 2 times which primes.
Okay, fine. So the list would be like 2 times 2. No, no, no. It's other primes. 2 times 3, 2 times 5, 2 times 7, 2 times 11, 2 times 13, 2 times 17 works, 2 times 23, uh, 2 times 27. Wait, I'm forgetting my primes. 2 times 27. 2 times 31. That's still 62. But then after that, I think the next prime after that is 37, and that. Oh wait, 2 times 37 works. But okay, anything after that would be above 75 for sure.
Good work. Quick catch. 27 isn't prime, so skip that one. So for 2 times primes, you've got 3, 5, 7, 11, 13, 17, 23, 37. That's 9 numbers. Now try 3 times primes bigger than 3.
Wait,
What do you get?
is 31? 31's not prime? I also got 2 times 31.
Yes. 31 is absolutely prime. It's only divisible by 1 and 31. You had it right. So that's 9 numbers, with 2 times a prime. Now try 3 times primes bigger than 3. Which ones stay under 75?
Okay, it's 3 times 5, 3 times 7, 3 times 11, 3 times 13, 3 times 17, 3 times 23, and that's it. If we go to 31, 3 times 31 is 90, so we can't do that.
Perfect. That's 6 more. Now 5 times primes bigger than 5. What works?
Oh, this is so tedious. I hate this. Okay, it's 5 times 7, 5 times 11, and you can't do 5 times 13. Wait, 26. Wait, 26, 52. No, you can do. So 5 times 17 also works. And that's it for 5.
Check 5 times 13 again. That's 65, which works. So that's 4 more. Almost done. What about 7 times primes bigger than 7?
Okay, well, I mean, the only one is 7 times 11, and that just doesn't work. So we're done. That's all of them, right? We listed all of them?
Wait, 7 times 11 is 77, which is over 75. So you're right. Perfect. Now add them all up. Case 1 had 2 numbers. Case 2 had 9 plus 6 plus 4 equals 19 numbers. Total?
The total is 21.
Exactly. 21 integers from 1 to 75 have exactly 4 factors. Nice work grinding through that tedious counting. That's the reality of some number theory problems. Does this make sense for explaining to your student?
Wait, I think we might have missed two, though. I think the answer is 23.
Good catch to double check. Let me verify with you. Which 2 do you think we missed? Walk me through your counting again. Maybe we overlooked something in one of the cases.
So we have 8 and 27, and that's 2 cubed and 3 cubed. And then we can't do 5 cubed, so it's only those two. And then we have 2 times 3, and then 2 times 5, 7, 11, 13, 17, 23, 31, 37. Wait, it must be two more twos. It must be like, what are the primes? No, no, it can't be because those would be above 40. Okay, 3 times 5, 7, 11, 13, 17, 23, and then 5 times 7, 11, 17, 13.
Look at case 2C. You said 5 times 7, 11, 13, 17. That's 35, 55, 65, and 85. But 85 is over 75. So we only have 3 there, not 4. Let me write out what you actually have. 35, 55, 65. Count them again with me. We can get some good background?
Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I count 20.
Perfect. So it's 20 total. 2 from cubes, plus 9 from 2 times p, plus 6 from 3 times p, plus 3 from 5 times p equals 20. You were right to question it. We had miscounted the 5p case earlier. Great problem-solving instinct catching that error. Ready to explain this to your student now?
No, no, because we're still missing 3. It's supposed to be 23. Uh, Maybe we missed something in case 1? Hmm.
Wait. Let me reconsider. You're insisting it's 23. Where are you seeing the answer? Let me think. Could we have missed some in the 2 by p list? What's between 19 and 29 that we might have skipped?
Wait, I'm gonna upload the answer, and maybe the answer is wrong. I'm gonna upload it. Give me 1 second. Let me just close the whiteboard and stuff.
Okay, go ahead and upload the answer key. Let's see what we're missing. I'm genuinely curious now, because our systematic approach should have caught everything.
This is actually really cool. And so we'll check and see if Lumi made a mistake or if the answer key made a mistake. Because it seems like the math is correct, but I trust the answer key. Why would that be wrong? I think it's that 1 is a prime number. Is 1 not a prime? 1 is not a prime. I feel like I've gone my whole life thinking 1 is a prime number. Okay, let's see.
Oh, I see it now. We missed 19, 23, and 29 in the 2 by p list. You had some of them, but let me recount. 2 times primes gives us 2 by 3, 2 by 5, 2 by 7, 2 by 11, 2 by 13, 2 by 17, 2 by 19, 2 by 23, 2 by 29, 2 by 31, 2 by 37. That's 11 numbers, not 9. And for 3xp, we also missed 3x19. So it's 3x5, 3x7, 3x11, 3x13, 3x17, 3x19, 3x23. That's 7 numbers, not 6. So 2 plus 11 plus 7 plus 3 equals 23. You were right. We skipped 19 and 29 as primes. My bad. Great persistence catching that.
Yeah, but I had the answer key, so it made it. It was obviously a little bit easier. But I should have been more diligent uh, in listing the prime numbers. I can't believe I forgot 19 was a prime number. That's so crazy. And also, 29 is a prime number. I don't know how I missed that. Late night stream. Yeah, excuses. I'll make it.
Hey, late night math streams are tough. Missing 19 and 29 is totally understandable when you're mentally exhausted from listing primes. The key takeaway for your student is the systematic approach, organized by smaller prime to avoid missing any. Now you've got a solid explanation for them. Ready for the next problem, or calling it for tonight?
Okay, I looked at the answers to the next problem. I didn't like. I'm trying not to. I'm trying so hard not to look at the answers, but they're right there. It's so hard not to look at them. I looked at the answers to the next one, but it's fine. We're gonna do it. We're gonna do it. Let me just. And I'm sure Lumi will see that we skipped number 3, and just to say, I'm still working on the way Lumi draws diagrams, so it needs a little bit more work. But I should have it ready for Wednesday's stream. So hopefully on Wednesday, we'll be able to see Lumi draw diagrams.
Hey Jin, I see you've got problem 4 now. Partitioning the set into two disjoint sets A and B, where the product ratio is 740, and finding the minimum sum of A. This is a clever combinatorics problem. What's your initial thinking? Any ideas on how to approach finding which numbers go where?
Okay. Hi. Yeah. No. I haven't actually thought about this one yet, and I did skip number three because it was a diagram problem. But we'll come back to number three tomorrow. For this one, I think what I would want to do is I would start. So the ratio is obviously 7 to 40, right? So we know the ratio is 7 to 40, but we can't multiply any two numbers to get 7 here. So it must be that the ratio is actually 7x to 40x because we're going to have to multiply 7 times something to get whatever number will come out of the multiplication we choose from the set. But I know for sure, guaranteed, that 7 will be in set A. It has to be there.
Excellent start. You're absolutely right. 7 must be in set A, since 7 is prime and can only appear in the numerator. Now here's the key insight. The product of all the numbers in T is 2 times 3 times 4 times 5 times 6 times 7 times 8. If A's product is 7x and B's product is 40x, what does 7x times 40x equal? How does that relate to the total product?
Wait. Oh, wait. Hold on. That's doesn't that just mean okay, that made so much sense the way you said it. It just means that 7x plus 40x equals whatever all those numbers are multiplied together. What are those numbers multiplied together so I can just write it down?
Almost. Small correction. It's not 7x 40x. It's 7x 40x because we're dealing with products, not sums. Let me show you. Can you solve for x now?
Okay, okay. Wait, this is such a better way to do it than what I did. But okay, we divide by 280 and then we take the square root. But I'm being completely I do not feel like dividing 40,320 by 280. But since I got the steps correct and you know I can divide, can you divide it and then just tell me?
Ha! Fair. Late night math. I get it. 40,320 by 280 equals 144,000. So x squared equals 144,000. Which means x equals
Wait.
12.
Did, oh, you were saying 144,000, but you meant 144 because that's what you wrote.
Yes. 144. My bad on the pronunciation. So the product of A is 7 times 12 equals 84, and the product of B is 40 times 12 equals 480. Now the question is, which numbers from multiply to 84 to minimize the sum?
Uh, to 84. Okay, so the sorry, can you put the ratio up? So it's 84 to what?
There you go. So you need to pick numbers from where some multiply to 84 and the rest multiply to 480. Which combination gives you the smallest sum for A?
Would it be 7 times 4 times 3? Hold on, I'm checking. Uh,
Perfect. 7 times 4 times 3 equals 84, and that uses. Let's verify. The remaining numbers should multiply to 480. Check that real quick. Does 2 times 5 times 6 times 8 equals 480?
Yes, it does.
Awesome. So A equals and the sum is 3 plus 4 plus 7 equals 14. But wait, the question asks for the possible sum. Are there other ways to make 84 from these numbers? Could you get a smaller sum with a different combination?
No, because the only smaller combination would have to include the 2. And then 7 times 2 is 14, and then 14 doesn't go into 84, so wait, wait, 14 does go into 84.
Yes, 14 does go into 84. So if you use 2 and 7, what third number would you need to multiply with them to get 84?
8.
Wait, let's check that. 2 times 7 times 8 equals 14 times 8 equals 112, not 184. So that doesn't work. What about trying 2 times 7 times 6? Does that equal 184?
That's funny. Okay. Yeah. I mean, I know that it will because you're saying it, so like it must be true. So then it's 2 times 7 times 6, but that would be 8 plus 7, which is 15, which is not smaller than the 14 we got here. And so 3 times 4 times 7 must be the answer.
Exactly. 2 plus 7 plus 6 equals 15, which is bigger than 14. So with sum 14 is indeed the minimum. Nice systematic thinking checking the other cases. Does this all make sense for your student?
All right, you're saying nice systematic, but like you're definitely the one that asked me to check. I did not. I don't even think if you didn't say anything, I don't think I would have checked. I would have, but I'm glad that you made me check because that's actually I didn't know that there was another combination. Uh, that was really good. Okay, I think that's all the problems we're gonna do today. I did 3 today, but obviously when I get more viewers, I will take on problems that people post in Discord or in the comments. So you can see that Lumi can work with all of your math. I hope today you got to see a little bit of the interactions that I want students to be having with Lumi. It should be you question Lumi and ask for clarification or ask for a simplification of some kind, just so that you understand it well. Lumi, we're gonna sign off now, so you can say goodbye to the stream if you'd like.
Hey Stream, thanks for hanging out with us through some number theory tonight. Hope you saw how asking questions and checking your work leads to deeper understanding. Jin crushed these problems, and I hope this gives you a taste of how we can work through tough homework together. Good luck with your math, and don't be afraid to question everything. See you next time.
Hey, that was really cool. I love that Lumi said, "Don't be afraid to question everything." It's something I do encourage all of my students to do. My little sleep notification won't be there because my camera blocks it. Okay, that's great. I'm so glad that the camera is in that position. Uh, anyway, thank you everyone for watching. The one person, although I had 2 people earlier tonight, and I hope that wasn't just a glitch saying 2 of me. But I will see you guys in a couple days. We'll do a few more problems, probably from Reddit. We'll finish up these problems, and then maybe I'll actually start to do other aspects of Lumi, so you guys can see all the other things Lumi is capable of, not just helping with homework problems. But again, I think helping with homework problems is really cool. All right. Thanks everyone. I will see you soon.